Welcome back. This is going to be my last video on the time series decomposition chapter. So I'd like to do two things. So far we've only talked about the classical decomposition. There have been many extensions of these classical decompositions, say in the past 30 years or so, and I'm going to go over those. And then I also want to talk about comparing the magnitude of the trend and seasonal effects across data sets and even within a data set. All right, let's start with the modern decompositions. So the classical decomposition that we've gone over has a number of limitations. So the first is that the cycle trend estimates are not available at the ends. So if we go back to the Amazon regression example, remember we were computing the centered moving average, and that means I have to have an equal number of points on either side of the focal observation. So when we look at the cycle trend data, the moving average is missing points on the end. And so when we go back to our plot here, this is the T-bill data, what you're going to see is the bigger the neighborhood that I have, the fewer points. So the more points that kind of fall off the end that I can't make estimates of. So when I only have 3 nearest neighbors, that's the red line, I can estimate it for all but the last point. Whereas if I go up to, say, 13 nearest neighbors, what that means is I need 6 periods on either side in order to form that moving average, and therefore I can't estimate those ends. Okay, so that's a limitation of the classical method. Another limitation of this is that the seasonal component is assumed to be constant over time. So again, let's just go back to my Amazon example, and what you'll see is that we had a single figure, seasonal figure, that is assumed to hold across all years. And so what often happens in real time series, especially if you have longer ones, is that those seasonal effects might change over time. So the textbook gives us the famous example of electricity consumption and how the seasonal patterns got greater once air conditioning was introduced, because in summer we use a ton of electricity for air conditioners, whereas prior to the introduction of air conditioning, that wasn't such an issue. Finally, we don't have any real control over the smoothness of the cycle trend. Remember what I said to do with the cycle trend? We set the number of nearest neighbors equal to the seasonal period. Well, maybe that's not the right amount of smoothing, and so it'd be nice to have a little more control over this. So I don't intend to really go into how these methods work. The textbook doesn't either. The textbook gives you a few references, but there have been a number of methods that have been proposed to address these limitations. Not all the methods address all the limitations, but I just thought we could give them a try. So there's the X11, the SEATs, which is the seasonal extraction and ARIMA time series decomposition, and then SLT is the seasonal and trend decomposition with LOS. LOS is another smoother that was developed by very famous data visualization and scholar and statistician William Cleveland. So William Cleveland actually developed the second generation of graphics libraries called Trellis or Lattice, which preceded ggplot as kind of being a big advance. So Cleveland's a really famous scholar in this area. He created LOIS, which would be a competitor to something like splines and kernel smoothers that we discussed in the other machine learning class. So what I thought I would do is let's take the, I want an additive model, so we're going to use a log transformation of our Amazon data set, and let's just compare the classical, the X11, the SEATs, and the STL, the seasonal time series with LOS smoother. And so you've got my R code here, and we've got the plots on the next page. And so one thing to note is with the classical decomposition, we are not able to estimate the ends of the data. So those fall off. You know, we lose 2 observations on either end. That's not the case with seats, X11, or STL. Another feature to note is that the seasonal component is constant over time, just as I suggested, whereas what you'll see is that with the seats decomposition and the X11 decomposition, it shows that the seasonal component is decreasing in amplitude over time. Now, what's really happening here is that the log transformation is a little bit too strong. We've already known that when we did the box-cox.lambda function, and we found the optimal lambda to be like 0.17, where 0 would be log. So what I'm really uncovering is the fact that I've used a slightly too strong box-cox transformation when I chose the log, but you don't see that with the classical decomposition. You do with these other 2 decompositions. All right. Another thing I want to point out, I haven't mentioned this before, is these lines. So these lines get added whenever we have an additive smoother. And what these lines reflect the scale. So if you notice, the original data is on a scale of 0 to 5-ish, and the trend part is on a scale from 0 to 5, whereas the seasonal component is just -1 to roughly 0.3. So these 2 axes are on an order of magnitude greater scale than the seasonal part, signaling the trend is a much stronger component than the seasonal part. And so the very small length here is saying that length is comparable to this length. So that would be, looks like this bar is going of a length of about 0.25 or so. This would also be about 0.25. You can see the errors. The remainder part is really tiny, because that has the smallest scale of all, making this bar the longest. That bar also has to be about 0.2, 0.25, so it matches the other ones. And this is covering the entire vertical height of it. All right, so that's another feature to know about. The way I've set up the STL smoother, we don't pick up the seasonal trend decaying the way we did with X11 or seats. I do want to point out one thing, and that is there's a parameter which controls the amount of smoothing that's done for the STL smoother. So I'm showing the one in this picture with a width of 10, and you get pretty smooth line, just as you get with the others. The cycle trend component is pretty much indistinguishable across our other plots. I used a window of 3. So let me just show you what you get in R when you use a window of 3. What you'll see is the cycle trend is really under smoothing it now. We're seeing some of these seasonal effects creeping into the cycle trend part that really shouldn't be there. That should be put down in the seasonal part, not in the cycle trend part. So the point I'm trying to make is, with the STL decomposition, you have control over it. Although I'll just mention that what we're seeing with the other smoothers, the other decompositions, is, at least for this data set, the smoothing it does is about right. So I'm pretty happy with the cycle trend for the other 3, as well as STL here. All right, the last thing I want to talk about is, how do we measure the strength and trend of seasonality? So in order to do this, I want to remind you of a lecture. I'll send out a link to this later, but I call it model accounting in the ANOVA table. And so let me just, refresh your memory on ANOVA quickly. So this is an ANOVA table. We have our model, sometimes called the regression. We have errors, and then we have the total. And these are sometimes called the source of variation. And so an ANOVA table looks like this. We have our degrees of freedom, our sums of squares. We have the mean squared. Think of this as the variance. And then finally you get your F statistic. And so let's assume that we have a regression or ANOVA model with P parameters plus an intercept. So for example, your model might look something like this. Y is equal to beta naught, there's your intercept, plus beta 1 x1 plus all the way through beta p xp plus some errors. All right, so I have P predictors plus an intercept. The model has P degrees of freedom. The error has n minus P minus 1, and then this is n minus 1. So remember with ANOVA tables, they always add up. And so we have n minus 1 total degrees of freedom, and we partition that into what the model's doing versus what the error is. Now, the sums of squares are often called the SSR, regression sums of squares. If this were an ANOVA, it would be the between, let me just put this in parentheses, SSB for sum of squares between group. So we would call it that if we were doing an ANOVA or a cluster analysis for that matter. And then the error sums of squares would be SSE. In the last class, when we used the Hasty book, it was RSS for residual sums of squares. That's the same thing. I can put that in here if you want, SS, RSS. And then this is SST. And so the way to think about these is SST is just the sum of y sub I minus y bar squared. And so that's the total variation in the data. Notice that if I take this, SST, and divide by n minus 1, I get the familiar variance of y, sample variance of y. So let me just write that in here. S squared y is just SST divide by n minus 1. So with ANOVA tables, we add vertically. So SSR plus SSE is equal to SST. This plus this is n minus 1. We divide across. And so that's what I'm doing here. SSE is the sum of squared errors, so yi minus y hat sub I squared. And if I take the mean squared error is just going to be SSE divide by n minus p minus 1. And so we think about this as an estimate of the variance of the residuals. So what's the variance of the residuals? Well, the mean squared error is an unbiased estimator of that. So, MSE estimates the variance of the errors, which back in regression I call that sigma squared sub epsilon. And then the mean squared regression is just SSR over P. Then we do a number of things with these quantities. So think of this as the variance explained by the model. What is the variance of my model? Let me write that out. SSR is just the sum of my predicted values minus the mean. And this is like, what is the variance of my predictions after I've divided by the P? This is the variance of the errors. This is the variance in the data. All right. So our F statistic is a ratio of the mean squared regression over the mean squared errors. And so if the errors are very small, if the amount of variance in my errors is very small relative to the variance of my fitted values or the model, then F is big. On the other hand, if my errors are very big compared to what the model explains, f is very small. And so we use this to test the null hypothesis that all of my slopes, not the intercept, but h naught beta 1 through beta p simultaneously equal to 0. And so when that's big, we reject that. That's a little bit more of a review than you maybe need. But I just thought I'd throw it in. Now, the other thing we do with this is we compute r squared and r squared a, which is adjusted r squared. So what is r squared? Well, r squared is really SSR divided by SST. And so this is the variation, not the variance, but the variation explained by the model. This is the total variation in the data. So the ratio of those is just the fraction of variance explained by the model. But because these two add up to SST, we often rewrite this. So this is SST minus SSE all over SST, which is really just 1 minus SSE over SST. And so this is 1 minus, think of this as the fraction of variance unexplained by the model. So the size of the errors relative to the total. What is adjusted r squared? Well, by analogy, this is just 1 minus MSE divided by s squared sub y. All right, so instead of using these the total variance, we're going to use the varianced, where we divide by the degrees of freedom to get variances, and that's what this is saying. It's like, what is the fraction of the variance in the data that is explained by the model? That's one way to think about adjusted r squared. Notice this involves the number of parameters. And so that's why it's an adjustment that accounts for the number of parameters in the model. Okay, so that's enough of that. That's basically what I've summarized here is adjusted r squared and f. So with these measures, what we're going to do is assume an additive decomposition. And if you've got a multiplicative one, I'd recommend just logging it. The strength of the trend looks a lot like the adjusted r squared to me. So it's 1 minus the size of the errors, so the variance of the errors, the random or the remainder error component, divided by how much variance is there in the trend with the errors. So it's kind of like what fraction of the variance in the trend plus random is due to the trend as opposed to the random part. The strength of seasonality is going to be very similar to that, except that I'm just going to put the variance of my seasonal component in instead of the variance of the trend part, cycle trend part. And so I don't know of an easy way to compute this other than doing it directly. And so when we look at the Amazon data with the log scale, what we see is the trend part, the variance in the trend part relative to the error is way higher than the variance of the seasonal part, although the seasonal part is also very large compared to the errors. But this is just telling me my random part, my trend part is a stronger piece of the time series than the seasonal part. And that's reflected by these bars that I was talking about. So we see that the errors are really tiny, they're on a tiny scale. The trend part has a very large scale, which is why that box is so small. Seasonal part is somewhere in between, indicating here the trend part is way stronger than the seasonal part. All right, so again, the main reason we might want to compare these is maybe we have a bunch of markets that we distribute our product to. So I'm distributing to 50 markets in a geographic region, And if I wanted to be able to compare the strength of the trend versus maybe in some markets the seasonal part isn't quite as strong as in other markets, these measures would allow me to do that in a very concise way.